Welcome back. Um, Today we're going to look at calculating the moment about a specific axis. In this case, the z-axis. We want to know what kind of moment we're creating about that axis when I apply a force at the end of that wrench. In the previous video, and I'll put a link up in the corner if you want to go see that, we determined the value of the moment about the origin, about this point, okay? Which is fine, and that's good information, and I repeated the values we came up with there. That's not the moment around that specific axis that we want. You know, what's the torque on the bolt we're applying, not what's the torque in a direction perpendicular to our force and position vector plane. So this moment, as you can see, it's got a big z component, but it also has a negative y component and a positive x component, so it kind of tilts off it a bit, you know. Now this particular example is kind of trivial, but we'll walk through the process anyhow, and we'll also run it backwards. You know, say if I want a specific moment, what does the force need to be? So we'll run it both ways. Because we're looking at the moment about an axis, the math becomes very simple, but it's worth walking through. Now, if you recall the previous video, I calculated my moment doing the cross product between R and F, and our moment, of course, is in Newton meters. I should have the units up there because our position vector is in meters and our force is in newtons, so the moment is Newton meters. And we calculated that moment by evaluating the determinant, and these are vectors. We determined I, J, K, and these are all moments. And then we had our R vector and our M vector, and we evaluated that determinant. So if you don't recall that, just go back to the last video, and given that I found this moment already, how do I find the moment about a specified vector? Well, or about a specified axis, I mean. Well, obviously we need to project from this M0, we need to project that onto the z-axis. And as we discussed, when we project, you know, I say project, you say, yes, dot product. So my moment about the z-axis, and because we're using dot product, it's going to be a scalar value, is equal to the M moment about our point, that vector which we calculated, times a unit vector in the z direction, okay, or dot, not times, dot. So m0 dot uz, and then of course uz is 0I plus 0J plus 1K. So that's, you know, why this becomes, those are vectors. That's why this one becomes kind of trivial. But if I do that dot product, I do the dot product between this and this, I get my moment z is 0I dot times the 9.18I, so that's just 0. And in the j, we have 0j, and we have 1.36. Well, that's still 0. And we have 1k times 2.60 plus 2.60, and that gives us, of course, 2.60 meters. Excuse me. That's kind of the two-step process. Ideally, we could do this in one step. If we want our moment z equal to our unit vector in the z direction dot the moment about the 0 axis, that is equal to u dot u sub z dot r cross f, and these are all vectors, okay? So I can write that as direction vector along the specified axis, u sub z dot that determinant that we calculated. And if I did all the math and worked it all out, what I end up with is, instead of the I, J, K up here, I can do the dot product between my unit vector and those component vectors, and what I end up with is just the magnitude of the things on the unit vector. So I end up in the top, I have 0, 0, 1, which is my unit vector dot ijk, and then I have the values of the r vector, which is 0.2, 0.02, and negative 0.06, and I have my force vector, which we calculated as negative 2.26, and these columns aren't lining up very well, are they? 12.8 and 7.5, that's that determinant. And let me just clean this up just a little bit. Not much, because I wouldn't want you to think I have good handwriting. This is 0, that's a 1. Okay, so I can evaluate that determinant easily enough, and that's just, well, I'd start out with 0 times the determinant of this, right? But that's going to be 0 because I don't have, I'm multiplying by 0. Again, the 0 in the determinant of these terms and these terms, that's going to be 0. So what I can do is it's just the last piece is that value times the determinant of this 2 by 2. I have this equal to 1 times 0.2 times 12.8 minus 0.02 times minus 2.26, and that is equal to 2.56 plus 0.452, and that gives me my 2.60 Newton meters as the moment about the z-axis, okay? And that's the same answer we got back here, 2.60. So that works out. Now let's look at this problem a different way, kind of work it backwards. Suppose I don't know the force, the magnitude of the force, I know the direction, and I want to find the force required to give me that 2.60 newtons meters moment about that z-axis. So I want to work this backwards, right? The problem here is find the force F pointing in the direction specified by those projection angles given a moment z of 2.60 Newton meters. Well, my problem, again, I'll write it out, is my moment in the z direction is equal to the unit vector in the z direction dot r, my position vector, cross F, my known force but with unknown magnitude. So here I know the direction, but the magnitude is unknown, okay? So I need to sort out the force F in Cartesian coordinates. I know that my F sub z is going to be equal to the unknown magnitude F times the sine of 30 degrees. And that's going to be 5.00 F. And I can project that down onto the xy plane, or parallel to the xy plane, and I get this F prime here. F prime equals F cosine of 30. And then given that projection down parallel to the xy plane, I can find the x and the y components pretty straightforward. So given that projection down parallel to the xy plane, I can find fx equals, and because this is going in the minus x direction, negative f cosine of 30 times the sine of this 10-degree angle here, and that's equal to 0.150 f, and the y component equals, and this is going to be positive, f cosine 30 for my projection times the cosine of the 10 degrees, and that's equal to 0.853 f. So now I can plug that into my determinant where or my equation where I know that 2.60 Newton meters equals the U dot R cross F, which I can write as 0, 0, 1. My R vector, we know from above, was 0.2, 0.02, and negative 0.06. And my F vector is negative 0.15 F, 0.853 F, and I know that's hard to read. My pen is getting kind of wonky on me here. And 0.5 F. And I can evaluate that determinant, and I come up with thing, these terms are 0, so it's just this term times the determinant of this here. And if I run through the math, I just get 2.60 Newton meters equals 0.1736. This would be meters times F, which is in newtons. And solving for F, I find that F equals 14.98 newtons. And if we go back and double check, we originally specified the F as 15 newtons. So we've kind of come full circle and got the same result doing the problem in both directions. Okay? It's using this determinant method is pretty straightforward. It simplifies the math. Trying to do this with scalar values gets messy. Just remember it's R cross F, so this, and then we do the dot product so we can put the appropriate unit vector in the top row. We put our R vector here, our position vector, and our force in that row, and it all works out. Okay, so thanks for watching and stay tuned for the next one. Bye.